Hi, my name's Alex. I'm from Rutgers, and I'm here to talk to you guys about file system aging. I assume you guys can hear me because it's very loud over here. Okay, so this is part of a work with all these fine people here called File Systems Fated for Senescence. Nonsense says science. And if you think this title's a little bit much, be glad we didn't go with our full title, File Systems Fated for Senescence. Nonsense says science. The essence of semperjuvenescence is coalescence. So, what does all this mean? Well, senescence means old age. Semperjuvenescence means being forever young. We did have to Google that one. And coalescence is the act of merging things together. So the idea behind this talk is that file systems don't have to age, provided you keep your data together. You can keep them forever young by keeping your data together. So, what do I mean by file system aging? Well, aging is fragmentation that happens in your file system over time. So you're sitting there using your file system and doing a whole bunch of operations, and time goes by while you're doing this, and eventually you start to see a decline in performance. A decline in performance. And what I hope to establish in this talk is whether or not file systems age, and how can we reproduce that aging, how can we measure it, and what can we do to stop it. So the first thing you might be asking is aging a problem? If you go to Google or something like that, and you ask, does my file system age? And here we've Googled, does my file system need defragmentation? You're going to get answers that look a lot like this one. Here we see that Linux's ext2, ext3, and ext4 file systems are designed to avoid fragmentation in normal use. If you do have problems with fragmentation on Linux, you probably need a larger hard drive. We could also look at the Linux System Administrator's Guide, and that says that modern Linux file systems keep fragmentation at a minimum. Therefore, it is not necessary to worry about fragmentation in the Linux system. So the basic idea is that if you go and you ask somebody who is a practitioner, an engineer who works with file systems, the answer that you're going to get looks sort of like nope. On the other hand, if you go and look at the literature and just type file system aging into Google, Google Scholar, you will see this work by Keith Smith and Margot Seltzer. And in this work, Keith Smith took daily snapshots of the fast file system for a period of 3 years. One was actually being used. And he determined that aging did, in fact, degrade performance. There's other work that suggests that when you're running benchmarks on file systems, you should make sure those benchmarks incorporate aging, otherwise you get non-representative results. So if you ask an academic or a researcher whether file system aging is a problem, you might actually get the answer, yep. So when we ask this question, we get two different answers from two different groups of people. So how are we going to resolve this? Well, let's do some science. How are we going to do that? Well, first thing we have to be able to do is we have to be able to induce aging in some way. In the paper that this is based off of, we use 3 different workloads. There's a developer workload, there's a server workload, and some synthetic workloads. I'm only going to tell you about this first one today, but I encourage you to see our paper to read about the other 2. So how does this work? Well, we basically want to simulate a developer. How do you simulate? What does a developer's day look like? Well, the developer starts out, gets some coffee. They probably pull the latest version of their project to their local machine. They do some stuff. Eventually, they get some more coffee. They will probably at some point pull the next version of the project to their machine. They'll do some more stuff. And eventually, they'll end up doing some more pulls. And basically what I'm trying to get at here is that we can simulate a lot of the developer's file system activity by just doing a bunch of git pulls, pulling one version, pulling the next version, and pulling the next version. And even a bunch of this other stuff that's in here, like, well, maybe not makes, but adding features and fixing bugs and stuff, that'll go into a commit the developer ends up pushing, and that'll be a commit somewhere else somewhere in this Git history and be pulled by someone else. So basically the workload that I'm proposing that we use to induce aging looks a lot like this. So more specifically, what we're going to do is we're going to use the Linux kernel repository from GitHub. We're going to do 100 git pulls in order. So we just take the first one, the second one, the third one, and so on. and we're going to measure the performance of our file system, and we're going to do another 100 git pulls, and we're going to measure the performance and see what happens. So you might be asking at this point, what do you mean by measure performance? How are you going to do that? So how are we going to go about measuring aging? Well, the way that we did in our work is we timed a recursive grep throughout the entire file system. So what we have here in these two little pictures, the top part is the logical structure of our little toys file system here, and the bottom part is the file blocks on disk. So each of these squares is the file block, and their color represents which file they belong to. If you do a recursive grep, it's going to scan through the file system, and it's going to read the blocks of the file in the order of the files in the directory and in the order of the blocks of each file. At some point, what's going to happen is there will be a file where the file blocks on disk aren't laid out all nicely sequentially. There's going to be a gap. It's going to have to seek. And this is something that we refer to as intra-file fragmentation. And this is going to take a little bit longer for this grep to scan through this file because it's going to have to perform this seek. Another thing that might happen as this grep goes along is it might have to seek from the end of one file to the beginning of the next file. And this is something that we refer to as inter-file fragmentation. So this is fragmentation where all the files might be completely sequentially laid out on disk, but they're not next to each other. And some people refer to this as file scattering. And then at the end of this whole process, what we're going to do is we're going to normalize by the size of the file system. What we're proposing to do here is do a whole bunch of git pulls, which change the size of the file system. So we have to normalize to make sure that we're being fair. So now I can start to answer this question: do modern file systems age? Well, here is what happens if we do this on ext4 on a hard drive. So this plot here shows, fortunately some of my lines don't seem to be coming through on the projector. That's okay. So on the y-axis, x-axis here, what we have is the number of git pulls we've performed, and it goes up to 10,000. And on the y-axis, we have the number of seconds per gigabyte that it takes to grep through this file system. I want to point out that, as you can see, it sort of slows down throughout the course of the experiment, and by the end, it's about 14 times slower. This happens really quickly. After about 100 or 200 pulls, it slows down by a factor of 2. After 1,000, it slows down by a factor of 4. And I want to stress, that's not really that many pulls. Like, if you're a developer, I'm sure a bunch of you guys are, that could be a few weeks or months of work. And also, in absolute terms, by the end of this, it gets really slow. The total size of this repository ends up being 1.2 gigabytes at the end of this. And it takes 15 minutes to grep through that, which is just slow to wait for. Okay, so how can we be sure this is file system aging? There could be some alternative explanations for this. Let's just go through a few of them, and I'll try and convince you guys that this is actually aging. So the first alternative is that the file system structure has changed in some way by doing all these git pulls. So, maybe there's more directories or more files per directory, files are smaller, something like that. Well, we can normalize for this by rejuvenating our file system. And all we're going to do is just copy the logical state of the file system to a newly formatted version of that same file system on a different partition. And then we can measure the aging again using a grep. And we just do this every single time we do one of these grep tests. We do the test, we copy everything over, we do a grep on the new unaged version of the file system. So what happens when we do this with ext4 on hard drive? Well, that line is much flatter, right? So the unaged version of this is substantially, shows much less performance slowdown. It does slow down actually on ext4 by about 60%, and we determined that this was because of a smaller average file size, which on ext4 does impact performance. We still see a difference between these aged and unaged versions of this experiment by about 9%, or 9 times. That's a little bit different. Okay, so next alternative. This is just something that ext4 does, right? Well, you guys probably can guess what I'm going to show you here. We did this on a bunch of other file systems. So here are Btrfs, F2FS, XFS, and CFS. They all show performance slowdowns over the course of this experiment, at least with our grep measurement, by about 12 to 22 times. XFS has a sort of performance anomaly when you freshly copy things over. It does some weird stuff. It didn't always do this, but on our experimental setup, which is our official experimental setup, it always did. So there you go. If you look at the aged version, you see it looks very similar to the way the other file systems work. But okay, so our next alternative is that this is a hard drive only phenomenon. And it makes sense to think that if you do this on solid state drive, that you're not going to have an issue, because fragmentation on solid state drive shouldn't really be a problem. It has much better random read performance. Well, if we look at XFS on a solid state drive, you see that, yeah, the curve is a lot flatter, and obviously everything's faster, but we still do see a pretty big difference between the two different versions of this experiment, and about a factor of 2. And this isn't just XFS. We can look at the other file systems, Btrfs, ext4, f2fs, and zfs. So Btrfs and f2fs look pretty similar to the XFS example, and ext4 and zfs, they kind of do if you squint. So with the ext4 and zfs, we have this weird performance where the unaged version, where we copy everything over, also seems to slow down just as much. So with these two file systems, there's something about the file system structure in particular that is causing the slowdown, at least not just aging. And in fact, this is because of smaller average file size again. And this is a sort of a function of the way fragmentation works on SSDs. And I'll try and explain that. So, well, why don't we just get right to that? Why do SSDs age? I'm trying to argue that this is a fragmentation issue, right? And SSDs have really good random read performance. Well, so let's talk about what happens on hard drive first, and I'll talk about what happens on solid state drives. So on hard drive, we kind of understand why this is an issue, right? If we have sequential logical block addresses, they are generally written to nearby physical locations on disk, on the same track, nearby tracks, something like that. And so we can just read them really quickly. If we have non-sequential LBAs, they could be written to physically separate locations on disk, and it might require a seek or something like that. And we understand why this is going to slow down performance. But solid state drives don't have an issue with physical locality. And in fact, when we wrote this paper, we didn't understand why solid state drives age, but there's this work here by Han et al. At ATC 2017, where they suggest that this is because of the number of read requests that are generated by fragmented data. When you have fragmented data, it generates a lot more read requests. So just to sort of show this visually, if we have logically sequential data, we can generate very few read requests. This happens at the block level and at the device driver level. And but if we have non-sequential data, we end up generating a whole bunch of requests. And solid state drives are fast enough that they can service these small requests faster than the OS can make them. So we actually get aging that's happening sort of because of a software level issue, not because of the drive. The drive doesn't care how fragmented your data is. But this is still an issue. And what's sort of interesting about this is that if we go to faster drives, we're going to get less of the bandwidth if we're trying to read all these fragmented data, because it'll be even better at servicing those requests. So, okay. So, yeah, that's solid state drives. Our next alternative is that you probably need a larger hard drive. So what I'm getting at here is that this is a sort of full disk issue. A lot of people think that about file system aging. The experiments that I've shown you so far have been performed on a 20 gigabyte partition. The repository size, which is the size of our file system, it just has this one Linux repository on it. It grows from about 290 megabytes to 1.2 gigabytes throughout the course of the experiment. So at its most full, it is 6% full, which suggests this is not a full disk issue. And in fact, we took ext4 on hard drive and we ran this experiment over again with a bunch of different partition sizes to let ext4 do whatever it likes. And in fact, it performed worst on the 256 gigabyte partition, the largest one we gave it. And we sort of expect we think this is because ext4 tries to make use of all its space and ends up spreading its data around a little bit. But it actually, ironically, makes it age slightly worse. But as you can see, they're all basically the same, whether we give it 4 gigabytes, 16 gigabytes. It doesn't really matter. Okay, our next alternative is that this doesn't really matter because of cache. So far, I haven't stressed it, but the experiments I've shown you have been performed on a cold cache. So we force our file systems to drop any caches that they're holding before we do this grep test. So the first kind of cache I'm going to talk to you about is deferred allocation, which you can think of as write caching. So this is where the file system has a little bit of time before it makes its allocation decision when it's writing out some data, and it can make a more intelligent allocation decision by waiting to see what else is going to be written. So this is generally limited to a small amount of time, a second or two, maybe as many as 5 seconds, but the aging that we're talking about happens on a much larger scale. We expect it to be over days, weeks, months, that sort of thing. So write caching can't help. Moreover, even in our compacted sort of Git workload, each Git pull, at least on hard drive, takes about a second or so. There's a limit to how much write caching can achieve on even that kind of scale. And we did leave deferred allocation on all our file systems, so this isn't really going to help. So disk cache, which we're sort of thinking of as read caching, it can help, but of course it's limited by available memory. If you can keep your whole file system in cache, then fine. Like obviously fragmentation is not going to matter. Nothing's going to matter. But as soon as you drop out of cache, we're going to see that this becomes, as soon as you don't have enough memory to keep everything in cache, we're going to see that you immediately have run right back into the fragmentation issue. So here is what happens if we look at ext4 on hard drive again. Here we are not flushing the caches, and so all of these lines except for the gray line and the bright teal line are warm cache versions of this experiment. And as you can see, what happens is when everything's in memory, they're super crazy fast. And then as soon as you run out of memory, you see an immediate and catastrophic slowdown as you have to start reading this fragmented data from disk again. I mean, because the data is basically going to be laid out exactly the same whether or not some of it's held in cache. And that's because deferred allocation really can't do all that much. And so, as you can see, it very quickly becomes slower than reading without any cache. This cold, unaged line here has no cache, but it has a good layout because we've just copied everything over and let the file system lay things out perfectly. So what I'm trying to get at here is that having some cache, if you don't have enough, is not as important as having, it's not as important as not aging, basically, is what I'm trying to say. Okay, so what I've been trying to communicate so far is that all the file systems we looked at, they aged by quite a lot, over 20 times on hard drive, and a factor of 2 or so on solid state drive. I also want to stress that you can use this, that we can use Git as a tool in this way, because Git is actually a real development history, and it allows us to very quickly induce aging by simulating years of use that people have actually done. And it doesn't take that long. It takes a few hours, maybe a couple of days, depending on the exact setup and how much you want to do. We've actually made versions of these scripts that we used available, Betrfs.org, and this would let you test your own file system to see how it ages, or if you have some benchmarks that you'd like to run on an aged file system, you can see how they'd actually work, and you can see what the effects of aging are on different workloads that you might be doing. So, at this point, I'd like to try and talk to you about how to prevent aging. I've kind of been trying to stress that, hey, look, aging is a problem. Well, what are we going to do about it? Well, let's look at the 2 different kinds of fragmentation I talked to you guys about before. The first is intra-file fragmentation, which is where blocks of the same file are not co-located. So pretty simply, we want to avoid breaking large files into small fragments, right? For the other kind of fragmentation, inter-file fragmentation, which is where we have related files, but those related files, their blocks are not co-located on disk. The way that we want to, the strategy we want to use to avoid this is to cluster those small files on disk when they're logically related. And we always use being in the sort of same directory as being logically related as a proxy. So before we talk about how to do these 2 things, let's talk about what we mean by large and small here, right? So I'm going to show you the following plot. This is a read length versus bandwidth plot, and this is on the actual hard drive that we used in our experiments. So what this plot shows is on the x-axis is the length of a read, and on the y-axis is the bandwidth that we get when we do reads of that length. And both of these axes are logarithmic, and this is not really surprising. If you do really small reads, you don't get a lot of bandwidth. If you do big reads, you get a lot more. At some point, you get diminishing returns because you're reaching the bandwidth of your device, right? The maximum bandwidth of your device. You might be surprised to see that solid-state drives have a pretty similar curve. This is the one that we used in our experiments. It's an order of magnitude faster, and it's flatter, but it's sort of similar. And so what we can do by looking at this curve is we can say, well, let's pick a point here that captures most of the available bandwidth, and we're going to pick 4 megabyte chunks. If we can use 4 megabyte chunks, well, here, let's see. If we can keep our related data in 4 megabyte chunks, we would expect, therefore, to substantially reduce aging, because we're always going to be writing and reading our data at a substantial fraction of our device's bandwidth. So how do we actually go about doing this? Well, let me show you a sort of warm-up example using Btrfs. We can't actually prevent aging with Btrfs, but we can reduce aging with Btrfs. And I'll show you guys how. So Btrfs is a B-tree-based file system, and what that means is that metadata in small files are packed into a B-tree, and large files get written somewhere else. Now, having the metadata in small files in this B-tree, especially the small files, they're put in this B-tree by path name, and so when you have files that have similar path names that are in the same directory, they get stuck in the same leaf quite frequently. So what that means is if we can make the leaves of this B-tree really big, say 4 megabytes, then we can keep our small files clustered in those 4 megabyte chunks, those chunks being the leaves. And we can test this because Btrfs lets us change the size of the leaves of the B-tree. So here's what happens. We're going to run our familiar git workload again on Btrfs, and we've changed the size of the leaves. It lets us change them between 4 kilobytes and 64 kilobytes, so not quite 4 megabytes. But what you can see here is if we use bigger nodes, bigger leaves, that we actually get flatter aging curves. So we get less fragmentation, which is what we expect. But there's sort of a problem with this. And that problem is that if we use larger nodes, we end up doing more writing. So if we have really big leaves and we make a change to one of those leaves, even if it's a small change, we read that leaf in, we make the change, we write that leaf out, right? So we get write amplification as a result. And we can test this as well. Here we did a very similar version of this git workload experiment, and we measured the amount of writing that we did between tests. So this should measure the amount of writing under this workload. So here on the y-axis, what we have is a number of blocks written in thousands in between every 100 git polls. And again, we see that bigger nodes lead to more writing. So you can see that we would get, if we used 4 megabyte nodes, we would have a lot of writing. So we have this trade-off, right? If we use a B-tree and we have bigger nodes, we get less aging, which is great, but we end up with more writing, which is not so great. If we use smaller nodes, well, we can solve the write amplification problem, but then we have more aging again. And this trade-off is inherent to B-trees. There's nothing you can do about it. Okay, so now I'm going to tell you what we can do about it using Btrfs. So Btrfs is a B to the epsilon tree based file system. So what's a B to the epsilon tree? So I'm going to use this little example here. So I'm going to imagine that we're trying to deliver packages. All right, we have our big central warehouse. This is like all of our changes to our file system coming into this warehouse, and we want to ship them out to our leaves, which are distributed throughout the country. So each one of these houses I'm going to show you is like a leaf. So in a B tree, anytime we get every time a package arrives at our warehouse, we just send it out to the leaf right away, right? And we have to do this whole read, modify, write business. If we have a whole bunch of changes that are going to all different parts of the B tree, well, we just send out a truck to every house, right? And you won't be surprised to learn that we end up sending out a lot of trucks and not that many packages on those trucks. This is the write amplification problem. In the B to the epsilon tree, it's like we have some regional distribution centers, regional warehouses. And we only send out a truck when the warehouse is full. So when our first warehouse fills up, we send a truck to whichever warehouse has the most trucks going to it, whichever regional warehouse. And then when that one fills up, we send a truck to whichever house is getting the most packages. Because we only send a truck when the warehouse fills, these sort of intermediate warehouses, intermediate nodes, if you like, they aggregate the changes. And what this means is that we can have as big leaves as we want, and we don't have write amplification. And there's a data structural guarantee that we don't get write amplification. I'm not going to bore you with the theory about it, but it's there. So Btrfs works just like, Btrfs to a great extent, but uses this slightly different data structure. So in Btrfs, you won't be surprised to learn, we use 4 megabyte leaves. So I can show you what happens when we run our aging workload, our Git workload on Btrfs. So here it is on hard drive. You can see that it is relatively flat, so that it is not aging over time, and that the aged version, the unaged version, you can copy everything over and you don't really recapture much of the performance because it's already laid out well on disk. Just to put this in perspective with the other file systems, these teal lines here are the aged versions of the other file systems I showed you, and the gray versions are the unaged versions, and this is Btrfs here at the bottom. So it's not like we're just slowing everything down in order to do this. Solid state drive is a similar story. We can, as you can see here, it doesn't really age over throughout the course of the experiment. And putting in context again, Btrfs is not totally optimized on solid state drives, but to be fair, neither are these other file systems. So you can see it still performs faster than the other aged versions. And yeah, here's a little pointer to that guy. And that's actually all I have to talk to you guys about today. So thanks. Any questions? Go ahead.
So is this any different from fractal trees, the epsilon tree?
No, fractal trees, well, sort of. So fractal trees are sort of the brand name of the epsilon trees. Some of the guys who are involved in this project were at Tokutech, and they branded it that way, but that was sort of a marketing decision. Yeah, it's the same basic idea. Yeah. Any other questions? All right. Well, thanks, guys.